I'm Marty Bollinger. I'm the oldest member of the Penn State bioinorganic group, other than one. I won't say who he is. It's a bit surreal to me that we got this many people sitting in this room which has no sunlight on this morning, on a Saturday morning, to listen to me talk for somewhere around 2 hours. No, sorry, hour and a half. So thanks for being here. This event is even more exciting and dynamic, I think, than our event was in 2012. And so, again, I urge you to take every opportunity to thank Karsten for all his hard work in this. So my objective today is to tell you about how we approach understanding enzyme reaction mechanisms using transient state kinetic methods combined with spectroscopy and calculations. I'm going to focus on the kinetics, but the other techniques are absolutely complementary. So what I'm going to do is present first the goals and challenges of a transient kinetic analysis of an enzyme reaction. The techniques, I'll tell you what we do, and I'll show you some pictures of equipment. But I'm going to really try to go quickly through this because this is really the topic of the practical part of the workshop. And I assume that anybody who is interested enough to want to see the guts of the instrument and talk about how they work has signed up for that part of the practical. And we'll see that from our personnel when they present during the next few days of the workshop. My primary goal is to try to get you starting to think about developing intuition in interpreting kinetic data, especially stop flow absorption data. It turns out that technique gives you a lot of information, but it's sort of hard to come by. There's a lot of different methods to analyze the data. There are a lot of mistakes made in the literature. And unfortunately, it really comes with practice. But I'll try to show you some of our experience, maybe prepare you to think about things when you face them in your own work. And then, depending on the amount of time we have, I'll give some examples from some of our recent work. Okay, so let's talk about the goals and challenges. Back in 2006, these two disreputable-looking gentlemen wrote a review article called Stalking Intermediates in Oxygen Activation by Iron Enzymes. So this was sort of a specialized, meant to be kind of a how-to manual for the type of work we do, because there were maybe 3 other people in the world who do the same type of thing, and we thought they might be interested in what we had to say. If you look into this abstract here, what you'll see is that in the objective of trying to come up with a how-to manual, we drew from an earlier review by Ken Johnson in the Enzymes in 1992, where he covered more generally dissection of enzyme reaction pathways by transient state kinetic methods. So that work is really almost a Bible it's the ultimate resource in this approach. And my students will tell you I keep a copy on my desk, and essentially every time somebody asks me a question, I'm getting out the manual here. So this is Ken Johnson. He was at Penn State. He actually was responsible for hiring me to Penn State, and he has a company called Kintec, which provides both instrumentation and the software, the key piece of software called Kintec Sim. And he also runs a course in early January at UT Austin, where he is now. And that course, it's a little pricey, but it's worth it. And his software, Kintec Sim, is also pricey. I'll show you that. I think a license for a single computer might be about $1,000. But we have several licenses, and during the course of the practical, I urge you to ask if you have questions about Kintec Sim. I know that Maria has extensive experience and will be happy to answer any questions. All right, so Ken, in his article back in 1992, set out the objectives here. Direct measurements of reactions at the enzyme active site are required in order to establish the kinetic and thermodynamic bases for enzyme specificity and efficiency. And that's really what we're really trying to understand, in addition to maybe figuring out how to design catalysts. That's something that metallobiochemists and bioinorganic chemists probably want to do more than the type of enzyme that Ken studied. So he said, we must redefine what constitutes proof of an enzyme reaction mechanism to include direct measurement of individual reactions occurring at the enzyme active site at physiological pH and with the natural substrate. So it's an ambitious goal, or set of goals. And so I thought I'd sort of elaborate that specifically to the case of bioinorganic chemistry and metalloenzymology. And so what we'd like to do is detect and then get electronic structural descriptions for each intermediate in the catalytic sequence. And as you all know, some of the reactions that we study in this community are really complex. So that could be a lot of intermediates. We would like a description of the transition state between each pair of consecutive reactant intermediate or product states, a delineation of the barrier heights and identification of rate-limiting steps. And then this is really, what I think people are most interested in. It's understanding how an enzyme in catalyzing a reaction lowers the key barriers relative to analogous uncatalyzed reactions occurring in solution. So this is what enzymology has focused on classically. But when you look deeply into metalloenzymology, what you find out is that there's a second level of question that's more important, and that is understanding how an enzyme suppresses other pathways that are invariably possible with the potent metalloenzymatic intermediates that we're seeing forming in this type of enzyme. So I think Mike Green's paper in Science in 2013 is a beautiful illustration of that. He has ideas about why hydroxylating, oxygenating heme enzymes, P450s, invariably have cysteine coordination to that iron. And what it comes down to is you basically have to generate a potent intermediate that can't react by pathways that you don't want to happen. And so the question is, how is that achieved? And it turns out that axial thiolate is key there. So really understanding what doesn't happen and how the enzyme prevents it from happening, because there are lots of pathways that can happen, is the essence of understanding how a metalloenzyme works. So there are certain technical and fundamental obstacles to this very ambitious set of 5 goals. A technical obstacle is the fleeting nature of intermediate states, and they might have lifetimes. In the type of chemistry we're interested in, microsecond to seconds, of course. If you're interested in photochemistry and in photosynthesis, we're talking about much shorter than that, right? So short lifetimes are a technical obstacle because you need methods that will take you into that lifetime regime, right? And so what I'm going to talk about exclusively today are mixing methods. It's a way to initiate a reaction by you leave out a substrate, you mix everything with one final substrate, and the reaction starts. And that's limited to reactions. You can only go, in terms of short time, into the microsecond, really for us into the millisecond regime. So I'm not going to talk about photoinitiation, which can take you obviously much faster than that. And I'm not going to talk about temperature jump methods, that sort of thing. These are the most general for the most different types of enzymes, but they are limited in time. Okay. So that's a technical obstacle, but the fundamental obstacle, and this is the most important thing to understand when you go into this, is the failure of intermediate states to accumulate due to unfavorable kinetics. So it's the problem that comes with slow formation, fast decay of states in a catalytic cycle. So we can illustrate that, and I'm going to use this enzyme as an example many times. Isopenicillin N synthase, originally studied by Sir Jack Baldwin. And what it does is it cyclizes, it does 2 cyclizations on this delta L-aminoadipolyl L-cystenyl D-valine, ACV, substrate to make the penicillin nucleus. So it's a classic reaction. It's an amazing reaction. And we, in the last several years, 6 or 8 years, have been trying to dissect this reaction. And embarrassingly, still haven't published on it, but that's going to be fixed soon. So here's the mechanism that came from the work of Sir Jack Baldwin. Incidentally, does anyone know where he got his first tenure-track position? Thank you. Who knew that? You guessed. Penn State, 1967. Stayed here, I think, 2 years. And then moved back and forth from MIT and Oxford. And there's a famous letter that somebody wrote to Jack Baldwin. I won't get into that. But okay, so here it has this reaction has 8 states in it. And what happens is the enzyme binds a substrate via cysteine coordination of the ACV. Oxygen adds to the iron and makes a ferric superoxide intermediate. There's a hydrogen abstraction from the cysteine, an inner sphere electron transfer reaction to make this ferrous hydroperoxide, which acts as a base to deprotonate the amide nitrogen to allow for cyclization of the beta-lactam, and form an iron 4, which abstracts a hydrogen atom, and then you get this recombination, radical transfer of the sulfur ligand acting as a radical to couple with the valine beta-centered radical, and then you get the product state that loses product. So that's 8 states, right, in a mechanism. But when Esther Tamanaha in our group began to look at this reaction, what she found is she can see 5 states. Okay, so she was able to detect this state and build it up to some extent, detect the iron 4 state, and by kinetics see evidence that there had to be an accumulating product state. And then it turns out that this is not actually a state in the catalytic sequence, that it seems to go somehow between these, and there might be an intervening state that is not accumulating, so it's not part of the kinetic mechanism. So what happens is this really interesting complex chemical mechanism collapses into this much simpler kinetic mechanism because these are the states that accumulate. And so the reason for that is that you have relatively fast formation of this superoxide intermediate, slow hydrogen abstraction, so this accumulates, but then right away this inner sphere ET is fast. There's then fast cyclization, so neither of these states accumulates, right here, because they're after, or they're before fast steps and after slow steps. So these guys don't accumulate. Then this does accumulate because there's a slow step after that, but then this one doesn't because it's fast. And so in kinetics, the important states are the ones that decay slowly. And the ones that decay fast and form slowly, we almost never know they're there, except that we write a mechanism on paper, and we know they kind of have to be there. Okay? So the problem is that we only get to see a few of usually a large number of intermediate states that we'd like to see. And so the general approach is we use stop flow absorption measurements to count how many accumulating states we can see and define their time scales. And then we'll choose times to freeze quench, to trap the intermediate states, and characterize them by a variety of spectroscopies. Now, what we would like to think as experimental scientists is that we could use tricks, chemically or isotopically modified substrates, site-directed mutants, changes in reaction conditions, to both to probe the mode of decomposition of accumulating states, but also, importantly, to build up states that don't otherwise accumulate. And we've been able to do this. We've had some success with it. But for every success, there's many failures. And in fact, I would have to say that overall, this hasn't worked too well for us. So really, it comes into the realm of computational methods to define, both to help us figure out what the intermediates that we see look like geometrically and electronically, but importantly to interpolate between these experimentally detected states to see what's happening as you convert from one detected state to another. This is an absolutely essential part of this process now, and it really is totally within the realm of computational chemistry, as Frank Meza was able to point out to us. And it's an iterative process. We usually take many years, unfortunately, to try to understand these reactions. Okay, so I'm going to present a kind of a dirty secret here, as Dean did in his talk. And it relates to this idea of understanding how enzymes suppress other pathways that are possible with the potent intermediates that we're talking about. So it turns out then that in no case in our experience has a detailed dissection of a mechanism, and we study oxygen and activating and CH cleaving, CH activating metalloenzyme intermediates. In no case have we failed to see the existence of multiple pathways. Okay, and this is a big, big challenge, practically speaking, to understanding reaction pathway. So we've seen things like heterogeneous reactants, where they both seem to form an intermediate but with different rate constants. And in this case, we don't really know whether these are in sequence and can interconvert. If they do, that must be relatively slow compared to the reaction of the reactant to make the intermediate. So we don't know if it's this or this, but we know there's two different reactant forms, and they form an intermediate, a common intermediate, with different kinetics. So we see two phases, and we don't know why. And to be honest, ensemble methods are really not going to tell us that. But single molecule methods are starting to, well, for many years now, have informed about stable, somehow different enzyme forms that turn over at different rates in a persistent way and can switch back and forth slowly. So that's in the realm of single molecule techniques. More importantly, we see all kinds of cases, almost every case when you look carefully, that a reactive intermediate that forms can be good at converting the substrate to the product here and making the product complex, but sometimes, and in some cases a lot of times, fails or makes a different product. And so we see this all the time, essentially every time when we're studying, for example, high valent iron intermediates, because they're so potent that they go different ways. And it's not totally controlled. Some enzymes control them well, others fail to. So the classic case of taurine alpha-ketoglutarate dioxygenase is a nice example of this. What we found when we looked carefully is that the enzyme with the normal protein-containing substrate makes a ferryl intermediate, and essentially 98 times out of 100, it succeeds in abstracting that hydrogen atom with this rate constant at 5 degrees, and then there's a recombination to make the hydroxylated taurine product that decomposes by losing sulfite. 2% of the time, 2% of the time it faces that hydrogen abstraction step, which is the hard step, and it fails. We don't know what happens, but we end up with an enzyme that didn't do its job 2% of the time. If we challenge the enzyme with the deuterium-labeled substrate, it changes. The reason is there's a really large, magnitude 50, deuterium kinetic isotope effect on abstraction of that hydrogen. Okay? So when the ferryl is challenged by deuterium, the rate constant slows from about 13 to about 0.3. And we then see evidence for this uncoupling pathway, this failure pathway. And now 25% of the time, the enzyme intermediate doesn't succeed in doing its job. And this happens all the time in metalloenzymes because we're talking about really reactive states. And as much as we would want to believe as biologists that nature's perfect, it isn't. It doesn't have to be. Okay, so what that means is if we're going to be faced with these divergent pathways, you've got to know how they behave mathematically and kinetically. So there's a little quiz here. So what happens when you have a reactant that converts to two products, P1 and P2? Simple partition. So what is the rate law that describes the concentration of product 1, product 2 with time? Well, it turns out that, I'll give you the answer, it's a constant times the initial concentration of the reaction at time 0 times an exponential function. Okay? And the question is, what is that constant and what is that observed rate constant? Does anybody know? Let's start, what's K observed for that process? Somebody from my group should know. It turns out that K observed is K1 plus K2. So if you sat and monitored the concentration of the product 1 as a function of time, it would be an exponential function, but the rate constant wouldn't be K1. It would be K1 plus K2. And that's because the time dependence of formation of that product reflects the loss of reactant, and the reactant bleeds down two different pathways. So it turns out that in terms of the observed rate constant, it's exactly the same for P1 and P2 because they're forming from a common intermediate. And so here's the concentration dependence for P1 and P2 in that simple case. And where the rate constant is reflected is in how much of the product you get at the end of the reaction in that irreversible sequence. So the C term here for P1 is the extent to which rate constant 1 dominates in these two. So this is, I just picked two rate constants. And with the 3 to 1, you get 3 times as much P1 as P2. But they form with the exact same kinetics. If you multiply this trace by 3, it falls right on top of that one. And that's the consequence of this bifurcating pathway. So now this is one little kinetic element. It's sort of a pattern. And if you can understand a few of these patterns, there might only be, I'm going to say, 8 to 10 simple little patterns. And if you get intuition about them, you can start to pick apart complex schemes by sort of confining to a couple of states, 2 to 3 states, and understanding how that segment behaves. And that's really an important part of the process. And in fact, Ken Johnson's review article does all this for you. It basically takes two-step sequences of various types and gives you the analytical solution, solves the differential equations that tells you the concentration of a given species at a given time. Okay? And if you can understand those and master those, you start to build those, put those together into a more complex sequence, and you can really get some intuition for this. And that's what I hope to start you doing. I mean, it's a lifelong pursuit. Okay, so the techniques. I'm going to rush through this because this is the subject of our practical. Stop flow absorption spectroscopy. The other reason to rush through is these are so simple compared to everything you've heard about for the last several days. It's basically a couple of syringes that blast two reactants together. There's a nice, efficient mixer, and it goes into some cell where there's a light source and a detector. And there's some different configurations that we use. So this slide gives you some vocabulary. You're going to hear this in the practical. I'm not going to. So there's two ways that we detect. In one case, we use a photodiode array detector where we shine white light from two different lamps. This is actually a commercial, an HP standard spectrophotometer, but it's not much different. We have a single lamp, I think it's a xenon lamp, that shines light through a collimating lens through the sample into another lens onto a grating and then spreads out the light. So you basically pass the white light through the sample and then you diffract it later onto a diode array, and each of those little elements tells you the intensity of light at a given wavelength, okay? And so if you put something that absorbs here in a wavelength-specific manner, what happens is some of these diodes see less light, and that's your spectrum. And it's a little bit complicated because the lamp, the light output is really structured. And then to an extent, the diode response is also structured. It's a little bit wavelength dependent. But if you have a good bit of light and, in the region of sensitivity to the diodes, you can mathematically correct all this. So you can get absorption spectra as a function of time on a millisecond time scale. So you're limited to millisecond. With this other detector, this photomultiplier tube, which everybody knows about, you can get microsecond resolution. But in practice, that doesn't do you much good in a stop flow experiment because you have this thing called the dead time. And that's the fastest you can get your reactants into the cell and get a reliable measurement. And that's typically a millisecond, a little bit less on commercial instruments. And after you use them a while, it's going to be a little bit more. But so in practice, getting microsecond data in a stop flow experiment in a commercial instrument isn't that big a help because you've already missed the first millisecond, right? But sometimes it's good to have that many data points. All right, so the PDA gives you a spectrum, but the problem is you basically shine the sun through your sample. And I urge you not to look at the light coming out of that light optical fiber bundle when you're doing a photodiode array experiment because, it won't have a good effect. It's very, very bright. And 5 years ago, I would have said there's a potential for photolysis of interesting complexes, and I would have said, but we've never seen that. And in the last 5 years, every single intermediate that we've characterized is photolytically sensitive. So it turns out, I don't know whether, what the statistics are, but everything that I'll show you today is photolytic. So you can still see it, but it'll decay faster in the PDA and possibly by a different pathway than when you use the more gentle single wavelength light that you use for single wavelength detection by a photomultiplier tube. Okay? So that's something that for the practical. This shows diagrams of the sample handling unit in our applied photophysics stop flow. We have 4 syringes, so we can do 2 mix experiments, no more than that. Biologic has a table at our symposium, not here at the workshop, but they're going to provide access and I'm sure lots of advertising for their instrumentation. And Mike Green actually has a biologic stop flow in his group. And one of the things that's interesting about that is it's 4 syringes with variable stepper motor drives, so you can push at any ratio. It's essentially infinite flexibility to mix things in different orders with different amounts. And that's a really nice feature of the biologic instrument. Kintec also makes one. It looks really crude, but it's really nice because you can take it apart and figure out what everything does. That was my first instrument when I started in 1995. All right, so here's some guts of the spectrometer. We put this in the glove box like the ITC in Dean's talk, and this is absolutely important. People who have tried to do anaerobic experiments outside of a glove box, it leads to a lot of heartache. In the glove box, it's relatively simple. So if you need to do oxygen-sensitive materials and you want to do stop flow on them, put the stop flow in the glove box. This is some pictures of it. You'll see this in the practical. Okay, so that's it for stop flow. Anybody want to ask any questions or wait to ask the experts later on in the week? Okay. The freeze-quench technique. Again, really simple. We're just going to blast 2 reactants together or more, sometimes 3 or 4, mix them as efficiently as possible. And now, instead of putting them into a detector, spectrophotometer, we're going to stop the reaction. So it's a stop time method. That is a pain in the neck because what it means is time resolution comes from multiple experiments, not from a single experiment, right? So that makes it a lot more time intensive. And we stop the reaction usually by shooting it into a cryosolvent, which would be cold isopentane or liquefied ethane, and you'll see both of those in the practical session. Here's some vocabulary, and importantly here, in a freeze-quench experiment, there are 3 time parameters to worry about. There's the transit time, and that is, back in this diagram, how long it takes between when it mixes and when it hits the cryosolvent. There's a quench time, and here that's how long it takes from when it hits the cryosolvent until the reaction actually stops. That's particular to a reaction and to the cryosolvent. But typically, it's going to be 5 to 10 milliseconds. So the time resolution here is sometimes disappointing. If you have a really fast reaction, you're kind of screwed by this method. But it turns out there's a recent development, not that recent anymore, which they call freeze hyperquench. So a number of groups have now worked on this. But the basic idea here is that instead of squirting into a cryosolvent, you actually eject forcefully onto these rotating, grinding metal discs. And the contact, the very narrow stream here, so low volume, high velocity, and the very cold wheels that are immersed in liquid nitrogen cools things faster. So you can get down to sub-millisecond quench times. And then you need to make use of that, you need a mixer that'll mix things in sub-millisecond. And so there's the various designs for microfluidic mixers. And you combine the two, and you get something that can get you down from, say 5 or 10 milliseconds down below 1 millisecond. But for technical reasons, that's more vocabulary there. For technical reasons, there's sort of this gap between a millisecond and 10 milliseconds. You can do 10 with the traditional freeze quench. You do below 1 with this wheel and hyperquench technology. But it's hard to get between 1 and 10. And so we're developing some mixers that'll allow us to do that. It's not a difficult problem to solve, but it's just seemingly people haven't really done that routinely yet. So we'll try to do that. And we had hoped to have this technology here to show you, but we ran into some stumbling blocks in acquiring it for our group. So you're not going to see this here. But if you come in 2 years, it'll be here. All right, so here's some more vocabulary. This slide shows you how you would sort of design a freeze-quench experiment to get the reaction time that you want, okay? I think it's self-explanatory. I'm just going to say that there are 2 types of experiments that we do. A single push, where it's really the hose volume and the flow velocity that determines the reaction time, because that's the transit time through that hose, and we're just shooting it through the hose. And so the length of the hose will be important to the reaction time, as well as how fast we push this plate down, how big the syringes are, so the volume they push per unit displacement. And that's all contained in here. The second type of experiment is if you want a long time, like 1 second, you don't want a hose that's like 7 meters long, so you use a hose that contains just enough to do your spectroscopy experiment, and you push it in there and let it sit for a while, and then you push it out. So that's the push, pause, push, as we like to call it here. And that introduces this delay time as an additional add-on parameter to the reaction time that you're trying to get in your reaction. Okay, so here's how you control the pushing, how fast, how far, whether you delay, and this is a computer, and I use that term loosely, but it works. This is all from Update Instruments now. Unfortunately, these guys are out of business, and from what I understand, you can't get their instrumentation anymore. And I see that as a disaster. I've been pushing Ken and his colleagues to develop an instrument. It's really simple stuff, but it looks like there's nobody who makes it. Biologic has one, and they're going to show it to us at the symposium, but it's complicated, and I can't even figure out what's going on in there. And the last time we had them in 2010, they weren't that great at explaining it. So if you're interested in freeze quench, we thought it important to have a commercial vendor that can provide an apparatus. But push these guys and find out, how it works and see whether you're interested, and let me know what you think about it. It looked good. It looked very slick. It seemed to work, but it was a little bit of a black box, whereas this thing is totally transparent. It's absolutely obvious how you're setting up these experiments. So here's some pictures of the freeze quench apparatus in our lab, and I sort of walked through a dummy experiment of what you would do here. Basically, it amounts to selecting the right line to get the right volume, the right transit time through that hose. You fire the motor, it pushes the syringes up, squirts the stuff from the 2 sort of reagent syringes into the aging hose. Then it comes out, you catch it in some vessel that has very cold cryosolvent in it. You're going to pack it down with this packer into this Mossbauer cell at the bottom. You're going to then take it apart, and under, it's not here, but under isopentane that's cold, you're going to put a cap on it. So you'll see how to do this in the practical, right? Is that true? People are going to pack Mossbauer cells. So, okay, the last technique is chemical quench. So here, instead of shooting it into a cold cryosolvent, we're going to shoot it into acid or base or an organic solvent or some other material. Okay, this is by contrast to the freeze quench method, where we hope we completely get a snapshot of whatever's in there at a given time. This thing destroys the enzyme, and often whatever substrate-derived intermediate species is there might be unstable. And so there's all kinds of worries about what happens after you shoot it into acid. You've got to take that into account. There's a couple important things that I'll tell you in just a second. Instrumentation, you can do this in the Update instrument, and we do. The problem is that you lose a lot of your reagent in the aging line. The beauty of this Kintec apparatus that's designed specifically for this kind of experiment is that you load samples in the side here, and they sit in this little loop, and it's like 12 microliters, a really small amount of sample. And then it's pushed through by buffer. So you're not wasting anything. You're using exactly the amount of sample that you need. So this is a beautiful piece of equipment. We have one. It's actually not in our lab right now. It's over in Freer. but I took some pictures of it. This is what the sample handling unit looks like. And somewhere, sorry it's a little dark, but down here is where you load the reaction loops. And it turns out that this is a young person's technique because the loops are so small and you've got to be able to see when you've loaded the right amount. And so I'd be taking my glasses off all the time. And so, yeah, it's better if you're young to do this. This is what it looks like from a distance, and you can see the stepper motor here pushing the syringes that usually have buffer. I forgot to note that once they go through this sample loop, they go, again, for some amount of time determined by the volume and length of this hose. And then there's a third syringe that has your quench, and that mixes here and kills your reaction, and then it comes out into an Eppendorf that you catch it in. And so reaction time is selected on Ken's instrument by this kind of crazy wheel here that has 8 reaction loops that you can turn so that it engages a different loop of a different length, and that'll give you the different transit time through. And you can also do push, pause, push here, so you can let it sit in there if necessary. All right. The chemical quench flow method. In our experience, in our type of science, stop flow and freeze quench is going to look at the cofactor. Those are the things that absorb and have spectroscopy associated with them, like Mossbauer, EPR, XS, all that stuff, the kind of stuff we care about. So CQF provides a complementary method that lets you look at the substrate and what's happening to that along that same time scale, right? So you can correlate what the cofactor is doing to what's happened to the substrate, and that is obviously a very important part of the equation, right? So, but chemical quenching is destructive. So there are two things that in kinetic analysis, if in an enzyme cycle, one comes to a product-bound, enzyme-bound product state, that counts. So if at the time that you had this thing, you've chemically quenched the reaction, you're going to see the product, right? Because it's there, it's bound. So kinetically speaking, it hasn't formed yet. In the Kintec Sim software that I'll show you, product hasn't been counted yet because it's EP, E.P, enzyme.product complex. But in a quench experiment, if you quench that state, you see the product when you measure it, typically by mass spectrometry. So it's important to know that there's not exact correlation between the kinetic simulations you're going to do and what you measure. You have to realize that that counts as product. And incidentally, in this type of experiment, an acid quench would probably hydrolyze the beta-lactam, so the whole thing falls apart, and then you've got to detect whatever it is it decayed to and know what it originally was before you quenched. Okay, so there's some caveats to this method. And mass spectrometry is, oh my God, I mean, this technique is, I mean, everybody knows this, how far this has come. It's incredible. We have 2 LC triple quads and an LC single quad in our operation, and you can detect ridiculously small amounts. It's almost annoying sometimes because you see things that, you know, really shouldn't be there. And importantly, if you can do any synthesis or you can buy commercially isotopically labeled compounds, you can do really almost perfect quantitation by adding an internal isotopically modified standard to do ratio analysis in mass spectrometry. So that's the gold standard for quantitation. That's what we typically do in this type of experiment. Okay. That's the techniques. Here's the important part, trying to understand data when you see it. This is really the challenge, and this is what comes with experience. So the goals when, I'm going to start with stop flow data. The goals when you look at stop flow data are first to determine the minimum number of states necessary to account for spectra or kinetic traces. And let me just say what a state is. A state is, to a kineticist, it's something that accumulates. If it doesn't accumulate, it's not a state. Well, it can still be a state, but you don't see it. And if you have 2 or more species that rapidly interconvert on the time scale of the overall flux through a reaction sequence, they count as a single state. So if you have 2 things in rapid equilibrium, they always form and decay in concert in exactly the same proportions defined by that internal equilibrium. So there'll be times when you'll have 2 things, but it's one kinetic state. Okay, that's important to know. So we're going to try to count the number of states, deduce time dependence of the species characterized by the individual features that are allowing us to tell they're there, and then formulate some minimal kinetic mechanism that relates to species versus time. And here, it's where we always, enzymologists and Ken, quite frankly, are biased to think there's some pathway, and we're conditioned to know that substrates can bind in different order. But once they get on there, we think everything has to be orderly and perfect. And it just isn't. In our field, it just isn't. You're always going to have to account for things that are going off where they're not supposed to, and protein that's not active, and all kinds of stuff like that. It's absolutely general. It's not an exception, it's the rule. Okay, so what are the tools in analysis of time-dependent absorption data? This seems dumb. Sometimes I think I should take it out, but visual inspection of time-dependent absorption data and intuition is surprisingly important. It can really help you to just sort of get a feel for what you're trying to see in data, okay? I'm going to turn the floor over to Alexei Silikov to talk about global analysis. Then I'm going to talk a lot about fitting and then simulations, and then give you some examples. So let's look at visual inspection. So here's a reaction sequence for an enzyme called AURF that Ning Li, Victoria Korbuk and Ning Li in our group studied, and now Bennett Straight and Bo Zhang and some others are studying still. And what this thing does is it installs the nitro group into the antibiotic called areathin. And its substrate is para-aminobenzoic acid, but here I show you the first intermediate that it makes, which is this para-hydroxylaminobenzoic acid. And it does a really interesting reaction where it takes a diferric peroxide intermediate and does a 4-electron oxidation that converts the iron cofactor from diferric with the peroxide bound back to diferrous. So this thing is fully catalytic, and it was a weird reaction that we discovered and reported in PNAS in 2010, I think. It turns out that if you take para-hydroxybenzoic acid, because it looks a lot like this intermediate or substrate, it will bind to the diferric form of the cofactor, and a lot of you will know that you then would get a charge transfer transition of phenolate to ferric ion charge transfer transition, which gives you an absorption around 500 nanometers. So if you take this resting AURF diferric enzyme and mix it with this substrate analog, you see spectra that look like this. You see a gain in intensity here at 500 from this charge transfer, and you see a loss of this band here at 360, which is from the mu oxo, so we think it displaces the oxo. So how many states do you see in there? Get some coffee. Great. That's right. Right. And so you see one state represented by this feature, one state that's characterized by that feature, and we think there are only two. Why? Why might there not be three? Very good. Isosbestic point. This is a smart group. Right here, it looks like there's no change, and that is indicative of a two-state transition, right? So that looks like just two states. And it's good to be able to look and say, that's awesome that you guys got that so quick. All right. Here's another enzyme called aldehyde deformulating oxygenase. If I hear anybody use this word, these two words together, you're going to be in trouble. This is not aldehyde decarbonylase. The enzyme was originally thought to lop the carbonyl group off this fatty aldehyde to make alkanes, diesel fuel basically, when it was reported in Science in 2010, I think. But it turns out it's an oxygenase that uses oxygen and 4 electrons to do a reaction that's not overtly redox, but still results in oxygenation of the formate coproduct. So we fought over names here, and we ended up calling it aldehyde deformulating oxygenase. Okay. So that's the reaction it does. It's a ferritin-like diiron carboxylate protein, and here's the diiron cluster. Okay. And so if you take the reduced form of that, the ferrous complex, with the substrate heptanal, let's say if we leave out the substrate, we mix that with oxygen-saturated buffer, we get this set of traces here. Here's the time. So it starts down here low and grows in. How many states? all these. So kinetically, when we're seeing that transition, how many things can you see in there? How many would you have to account for if you were going to simulate what's going on here or analyze what's going on? 2. You see something that doesn't absorb much. This is actually probably contaminating oxygen that gave us a little bit of the product before we started. And then it grows into something that absorbs. There's no evidence for anything more than 2 there. But if you had the substrate there and you mix with oxygen, it looks like this. So this actually goes up and down. So here, 0.1 is this red one. 100 is the purple one. But in between, we've got stuff going on there. So it goes up and down. So how many states there? Well, it's more than 2, right? It's got to be 3. Might be more. Maria will show us in a second it's more. But it looks, by visual inspection, there's a reactant state that doesn't absorb, a product state that absorbs. It looks pretty much like this one. But in between, there's an intermediate that absorbs around 450 nanometers. Turns out what we think that is this peroxy hemiacetal intermediate that normally in the productive reaction cycle is waiting for an electron, but in our experiment we didn't give it an electron. So it goes here and gets stuck. And Maria and Ning showed that if you, and now Lauren have shown that if you supply an electron with by various sources, it will go forward and make the formate and alkane product. So we think that's what that is, and it's an intermediate that decays slowly. And here's a case where this is what it looks like under the white light. The kinetics are different if you put it under the photomultiplier tube, because this thing is it's pretty photolytically labile. Okay. And okay, isopenicillin N synthase. I told you we had intermediates here detected by ESTA. Here are some spectra. Okay, so these are different spectra. This is what changes after the mix with time. Here is, well, I'll tell you that the thing that we subtracted is like 1 millisecond, and so that would be a flat line. 2 seconds, it's a flat line, but in between it goes up and then it goes down. How many states do you see in there? This one's a little trickier. More than 2. Was that based on logic or just that I said it was trickier? I think that's right, but I would tell you that I probably got this one wrong at the time because I thought, well, this is really 2. It's something, it could be 3. We don't know whether what it decays to is the same as what it started as, right? But it doesn't absorb, and then it does, and then it doesn't. That could be 2 states. But there's actually clear evidence that there's at least a third one in there. The reason being, for it to be 2, the absorbing thing, you'd have to be able to multiply each of these spectrum by an appropriate factor, and it should fall on top. It should always be the same. If there's only one absorbing thing in there, there's more or less of it, but the spectrum's the same. And clearly that's not the case here at 2.5 milliseconds, right? There's something going on out here, all right? And so that became more obvious when ESTA used the deuterium-labeled substrate, and now her first spectrum looked like this. The characteristic 500 nanometer feature, which turns out to be the ferrule intermediate, doesn't come up at all. Like here at 2.5, it's already pretty huge. There's a little something out here. But here at 2.5, that feature's not there, but we still have this absorption and more of it way out here. So it turns out this is the ferric superoxide state, and it weakly absorbs, so it's trying to stay under the radar there. It doesn't accumulate much, and it doesn't absorb much. So it's hard to see. So I think, if I'm not mistaken, I didn't realize it was there when ESTA first started showing us these data. But it is there. And so the thing that absorbs out here is this guy, and the thing that absorbs, here at 500 is this guy. And you can tell that when she uses substrate that's labeled here, it retards formation of the thing that absorbs at 500 nanometers, so it slows it down. If, however, she labels the valine portion, she actually stabilizes that species, so it forms initially at the same rate, but then it decays much more slowly. So that's the deuterium kinetic isotope effect for the ferrule pulling off the hydrogen here, and the deuterium effect for the ferric superoxide pulling this one off slows formation of the ferrule. So you could diagnose where these things are in the sequence, but the first thing was you had to know that they were there. Okay. So the next, so that's sort of intuition. Alexei's going to tell us about global analysis.
Okay. Yeah, I'm using the mic because I didn't want to switch. So, yeah. What basically we learned, let me see if this works. Yes. So, what we have as experiment is something of a 2D data set. And we have to connect that to a model that we have in our minds of your boss or of your competitors, never mind. You want to prove or disprove. Nevertheless, these are two different worlds that you want to connect, okay? And the way to do this is pretty tricky. And before I'm doing anything else, I want to point out there is not a single program that can do it for you. You have to be the one who supplies some input. You can't just press a button and it gives you the result and you publish it. So that's the thing. Okay, no, it works good. Very simple way to analyze. I will talk about the stop flow data most of the time, although all this analysis can be worked out for any other EPR, Nussbauer kind of data. So anyway, if you have known components that you know are there, and you truly believe that's the only thing that moves around in your experiment, what you can do is just do least square fit of the amplitudes. You just vary the component for different type steps. And you form some kind of kinetics out of that. And that's good. The only problem is you already know half the story to start with, the spectra. And that's usually not the case. In fact, in many cases, like Marty pointed out, you don't even know how many states are there. What do you do with this? And there is actually a very elegant way to figure out in 80% of times at least. Well, plus minus 20. Okay, so it calls single variable decomposition. And the theory goes that any 2D data set, can be decomposed into 3 matrices. One, if we talk about the absorption spectra, time dependence of absorption spectra, the first one, we call U, will be your abstract spectra. Columns of this matrix will represent the spectral components, abstract spectral components, all right? Second one is a diagonal matrix, and diagonal elements correspond the magnitude of contribution each of those abstract spectra have on the time dependence. And the last one, basically, it's just the other dimension, which is the abstract concentration, how the things depend in time. And one thing which is really important to know, these are abstract spectra. They have nothing to do with reality, well, at least in this simple way. They do have contain information about your actual components, states, but by themselves, as you see, they look kind of weird, okay? So what is it used for? Well, one thing which is quite cool, I think, is that just by looking at the S matrix and how many elements are substantially above 0, you can actually tell how many components are changing within this thing. So, for example, in this particular case, this is P450's reaction. We only have 2 singular values which are well above 0. The rest is basically flat. So we can say in this particular case, and you can actually say by multiplying this basic point 2, but this is not the point. We only have 2 components. You can also look at this by just plotting out different columns of these U and V matrices. 2 of them, in this case, are quite well. They kind of resemble something. And the third one is already just noise. In fact, it's actually kind of funny. You see the noise comes big and then flattens. That's just when spectrometer switches the range, just that. But you can see what kind of changes it can make. Oh yeah, and that's actually a very important point. Any baseline change in your spectrum is a signal as well, right? So conditioning your data set before you do all this is also important. Okay. First thing, yes, we can know how many states are there. Well, it's not working all the time. Again, the baseline, it's not always easy to correct. You can have some states which are accumulate like 1%. Well, there will be very small contributions there, and you will have to guess whether it's real or not. Okay? But it's useful just to start moving with your data. The second thing we can do with this theory is so-called target test. That's something I learned recently is actually used for facial recognition in the surveillance systems. You have targets, and you can figure out if these targets are in the crowd. You can do the same here with spectra. So the way it goes, you believe you have n different contributions to your spectrum. Let's say 3. Okay? Using those columns, you can construct a projection operator, and on that, you multiply a target spectrum, which is a column. And then you get a result, and you compare result with the target. And if those two match each other, like in this case, for example, this is ferric state, the steady state of the P450s, they match pretty well, so I can say that in my data set, we have a ferric state. Well, I know that anyway, but it doesn't matter. Compound 2 and others, this is the final state of the product, of the reaction in this particular case. Yes, it is there. I know that because target and the result matching up pretty well. Compound 1, this elusive state which was studied for years and decades actually, and was a big discussion in the literature and very important one as well. Do we have it in this state? Well, we don't. You can see that the target and the result don't match at all. So this can give you relatively simple yes and no answer. Of course, you need to supply some targets. That's important. But if you don't have them for your system, maybe you have some prototypical system or something similar. Like, for example, P450s have counterpart called chlorperoxidase. It has similar cofactor. It's much worse as a catalyst. States can be accumulated. But people believe that the spectra are quite similar to the ones in P450s, so we can use them as a target test. And that was, in fact, what has been done for compound 1, at least to get some idea where the spectrum goes. So this is pretty useful. And the third thing which you can do, and now it gets a little bit more complicated, you need about 10 lines of code in MATLAB, calls global analysis. So your spectrum is technically a sum of all the contributions that change in time, which you can arrange in sort of matrix with epsilon that contains all your spectra, and C, which is the concentration profiles. And that's what experiment gives you, supposed to give you at least. And SVD provides you technically the same thing, although in the abstract world. You have U and V, the abstract spectral and abstract concentrations. And we need to we need to connect those two worlds together, abstract and real world. We do this by introducing a little trick. We apply this matrix R, which is our conversion matrix. We don't know it. That's the problem. And because we don't know it, we have to model it somehow. In the kinetics, usually things follow exponential laws. They're relatively easy to model. Of course, a lot comes from the researcher. Of course, you need to know the model or think of a model. But once you be able to model this, you can actually reconstruct your spectra. And you can do it iteratively, and this way you can actually get some really good idea how your spectrum is supposed to look like. And how you do it? Well, it's, as I said, 10-line code in MATLAB. You get a kinetic model. You just construct a matrix of concentration profiles. Based on that, you construct the this R matrix, which you use to reconstruct your spectra, and then sort of make a model of your experiment. And then you compare that model with the real experimental data. If it is bad, well, you just change kinetic rates. That's to start with. Try this iteratively if it fits better or not. If not, well, you have to change the model. And once it goes good, yeah, you got it. This is it. You publish your paper and you're happy. And everybody's happy. So, and there's a really good example how it's been done in P450s. It's really good work in Organic Chemistry 2010. in our group where people actually figured out, after decades of research, I want to point out, how UV spectrum of compound 1 and P450s look like using this method. And I really encourage you to look at this. And it has a really good description how this whole thing goes step by step. I think with that I can bring back.
Okay, thanks, Alexei. I think this is potentially, well, and in reality, extremely powerful. But this thing I've been telling you about, the multiple and branch pathways and convergent pathways, is what really kills or limits the broad utility, or it makes this not a panacea to understand mechanism. And it's because it's at this stage model dependent, and a lot of times we want to have a simple model, and we will typically apply a simple model, and these little branches that we see can confound this analysis in really severe ways. But this is an important part of the arsenal. Okay, so the next thing I want to tell you about is just a more standard way of analyzing single wavelength traces, because sometimes even states that are not that might not absorb and are not represented well in that spectral matrix can be uncovered by mathematical fitting, nonlinear regression of kinetic traces. So this is still really important. What I'm going to tell you is, at the end of the day, to have success, you've got to simulate by numerical approximation. That's always going to be the final analysis. But you're never equipped to do that right off the bat. So fitting is really a way to pull out these little pieces that I started to talk about and try to figure out what's going on in these little segments on the pathway to building up a full kinetic mechanism that you then use Kintex Sim to simulate all your data by a single mechanism with a single set of rate constants. Okay, so this is on the pathway, but rarely is it the final analysis. Okay, so let's talk about fitting. Here's an enzyme reaction. Myoinositol oxygenase takes myoinositol and cleaves between C1 and C6 to make D-glucuronate. This is an interesting 4-electron oxidation, cofactor independent with a single equivalent of oxygen. And back when we started studying this in 2004 or so, there wasn't anything known about how this would work. It was really bizarre from the standpoint of precedented iron chemistry. Well, it turned out that our biochemical work and the structure by Ted Brown at University of Auckland in New Zealand kind of showed what's going on in this system. And it happens to be the first example of a diiron oxygenase that uses a mixed valent diiron center. So this iron 1 is ferrous, and this iron 2 is ferric. And in many of these enzymes that have diiron clusters, that state is not very stable. But in this family of oxygenases, it's actually quite stable. It can build up to 70 or, Maria, 90%. So what happens is the ferric ion acts as a Lewis acid to bind the substrate and probably deprotonate C1, and that activates this C1 carbon-hydrogen bond. Oxygen then binds to the ferrous site and makes a ferric diferric superoxide intermediate that pulls the hydrogen off. So that's how it starts. What happens next is not as clear, and we haven't made very much progress on this, to be honest. But so this is what it looks like. Now, it turns out Gongqing, a postdoc with us, discovered that when myoinositol binds, it causes this change in the absorbance spectrum. This is the delta, starting from the form that doesn't have the substrate bound and adding the substrate. When it binds, it gives you a negative feature at 500 nanometers and a positive feature around 400 nanometers. And so you can use that to monitor the kinetics of substrate binding. And Gong did that at 4 different concentrations of substrate, and he got these traces. Okay, so what do you do once you get those? Well, you fit them. And in this case, we actually plot this as a normalized delta, which is a little bit cheating, but it allows for the simplest type of fitting where it's just an exponential decay, right? And so when he fits those, he gets a set of K observed rate constants. Turns out that Ken Johnson's article will tell you that the dependence, the concentration of free enzyme over the total enzyme at any given time is related by this expression where K1 is the binding constant for the substrate, the 1 over the dissociation constant, and then substrate concentration, and then here's the exponential dependence. So this tells you how much you're going to get at equilibrium. That tells you the time evolution toward equilibrium. Okay, and this is another thing that's maybe a little counterintuitive, like that bifurcating pathway issue. Turns out that the observed rate constant for approach to equilibrium is the sum of the effective first-order rate constant for the forward plus the first-order rate constant for the reverse. Okay, so what that means is if we pull out observed rate constants and plot them versus substrate concentration, it's going to be a slope with rate constant of the second-order rate constant for binding, and an intercept, which is the first-order rate constant for dissociation. So from that single experiment, you can get K on, K off, and KD in favorable cases, and this was one. So it turns out that the K off was about 0.1 per second, K on is about 0.24 per second. You take the ratio, you get a KD of about 400 micromolar. Okay, and there's no evidence that there's any complexity. Single-step binding. So this is another one of these little motifs, little segments that you have to understand how would it work, right? And that will give you the intuition to build up. But the equations, you don't have to solve these differential equations because Ken already did it. And actually, he just compiled what other people had done in his review article, okay? So then Maria didn't discover, but showed that an enzyme that was reported in JACS in 2012 called PHNZ or Z is the second example of a mixed valent diiron oxygenase, and it was found in a pathway for degradation of the common phosphonate 2-amino ethyl 1-phosphonic acid to glycine and phosphate. Two-enzyme pathway. The first one is an alpha-ketoglutarate dioxygenase that hydroxylates. The second one cleaves this carbon-phosphorus bond, and that is a mixed valent diiron oxygenase. And so we showed that Maria analyzed by sequence, and we showed by structure, and another group has now published a better structure that shows actually, is this the citrate-bound form? Looks like the citrate-bound form. Okay, so this isn't the actual substrate, but it binds to iron 2, just like in myoinositol oxygenase. This structure was solved by Amy Boll and Mahesh Lingarahu here at Penn State. And so Maria then did the same experiment that Gong did with MOX, and she got these traces at different concentrations of the substrate. When she plotted K observed versus concentration, it curved. Actually, Binia did this too, so these two have collaborated on this. And so the curvature is different from what we saw with myoinositol oxygenase, and it suggests a two-step binding mechanism. And if you look, you get out the manual, Ken Johnson's review, and you'll find this, rapid equilibrium followed by some kinetically significant isomerization step, whatever that might be, lid loop closure, for example. And what you see is it behaves according to this equation. And from that, you can pull out the reverse rate for this conformational change by the intercept. And from the curvature, you can get both K1 and K2. Actually, you get the product of the two. So this is the apparent second-order rate constant for substrate binding. And it gives a KD observed, what you see as a result of this two-step equilibrium where it binds weakly but rapidly first, and then the enzyme locks it in place. That gives you the low KD of 74 micromolar. Okay? So this is another type of segment that you'll encounter, and you have to understand how that works. And Maria was rigorous enough then to use the EPR spectral perturbation to do a thermodynamic experiment at equilibrium and determine the KD, and it came out to about 50 plus or minus 10 micromolar. So that agrees well with the 74 micromolar from the kinetic experiment. Okay. All right, aldehyde deformulating oxygenase. Remember, I showed you these spectra, and we said there are at least 3 states in there. Well, when Maria got some really nice kinetics here, she got the blue trace, and she said, okay, let's assume there are 3 states. Reactant, which doesn't absorb much, goes to intermediate, that absorbs a lot, goes to product, doesn't absorb much. And she fit it by this equation which describes the concentration of the intermediate I in an irreversible two-step sequence from reactant to product. To convert that to absorbance, we actually have to multiply here by the molar absorptivity of the intermediate. So that was a mistake in the slide. And so what happens is Maria saw that it didn't fit very well. I mean, I think anyone can see that, right? That's a terrible fit. And so what we reasoned was it looks like there are two reactant states, because you can sort of see a second phase in here. So it looks like there's two reactant states, which we call R and R prime, that both can convert to the intermediate. So all that means is, because they're convergent, it's just two different components that both look like this. And when she fits it that way, she gets essentially a perfect agreement with the data. So what this suggests to us is that in this formation of this intermediate, by mixing of the diferrous form with substrate bound in oxygen, somehow this thing is complex. There are two states. And what might they be? Well, the simplest idea would be it's just not saturating its substrate. So you have a substrate-free form that had to bind substrate first and then go on, and a substrate-bound form that can go on directly. But the issue is that when we titrate up the substrate, we never get rid of that second phase. So we think it has to do with different modes of substrate binding or different conformation of the protein. We don't really know, but we know that state is unequivocally there. We can see it both in the time-dependent Mossbauer data and in the stop flow data by Maria's fitting analysis. Okay, so that's this case where two different forms of the reactant somehow converge on an intermediate, but it could be this as well. We don't know. All right, I think this is the last example of how fitting can inform developing a mechanistic sequence for the more rigorous simulation analysis. You're going to see two talks on this in the symposium. This is an enzyme called carbapenem synthase, and what it does is it takes this 3S, 5S carbapenem produced by CAR-A and epimerizes the 5 position, which allows putatively for a subsequent desaturation that we haven't been able to make happen yet. And so the mechanism, it turns out that we published it, Wei-Chen Chang and Amy Boll figured out in this year in Science. What happens is a ferryl intermediate forms, it pulls a hydrogen off, then a tyrosine donates a hydrogen atom to the other side of the substrate. And that epimerizes this chiral sp cubed hybridized carbon. So it's a kind of a novel non-redox reaction. And it turns out that the enzyme's dead at this point. It doesn't do anything else after that unless you supply a reductant to reduce the tyrosyl radical in the ferric center. So it's a one-turnover stoichiometric reaction. So evidence for this is for the tyrosyl radical comes from absorption data. And what Wei Chen did was he mixed the enzyme iron 2 substrate 2-oxoglutarate complex with oxygen-saturated buffer and saw rapid development of this sharp peak at 410 nanometers. A lot of people in the audience will know that's a tyrosyl radical. It's absolutely obvious, especially when you see the shoulder at 390 nanometers. And so Wei Chen can measure the height of that by just some mathematical analysis to sort of extract out the concentration of that species or absorbance proportional to that concentration, and he gets this trace, okay? So how many states? Well, we thought there's a reactant, and there's a state that has a tyrosyl radical, and then there's a product state that doesn't have a tyrosyl radical. So we thought 3 states, and Wei Chen did the fitting. He said reactant goes to tyrosyl radical, goes to product. That's A to B to C with these rate constants. There's the equation, and the fit is lousy, right, especially here. So what it looks like, now keep in mind this is a logarithmic time axis here. So it doesn't look the same as it would on a linear axis where it would just go up and down. It looks like there's a lag here in the green, but that's actually just the consequence of the logarithmic axis. A to B to C does not give a lag in formation of B, because you start with A, and as soon as time starts, it starts making B, and it's fastest at time 0, right? However, the red trace reflects like some delay, some induction period where you're not getting that tyrosine radical. So what Wei Chen figured out is there has to be an additional intermediate before the tyrosine radical, and that's A to B to C to D now, where the tyrosine radical is C with 3 rate constants. And here's the expression for the concentration of C. To turn that into absorbance, again, we just have to have molar absorptivity. Okay, so that's not the exact equation used in the fit. But when he fit it by this more complex equation, clearly fits a lot better, right? So he's accounting now for that lag. And it turns out what that intermediate is the ferrule intermediate. And from the fitting, he could tell approximately the time dependence of that ferrule. And so we could then go and do a Friese-Quench-Mossbauer experiment right there at the maximum of that. And lo and behold, there were peaks for the ferrule intermediate maximizing right at that time. So he could tell really where this unseen prior intermediate was and would accumulate by the mathematical analysis of the shape of that trace. And that's how fitting is still really important, even though, in the end, the final analysis is going to be done by simulation. And if I get to the example at the end, which is not looking good right now, then I would show you how the simulation of all the data from stop flow and freeze-quench EPR and freeze-quench-Mossbauer and chemical quench flow, it's all done by a single mechanism, and it's totally trivial. Once you know what the mechanism and rate constants are, it's, you plug it in. So that it's really easy. But so what this showed is that we have this ferrule going to this state, and this, chemically reasonable state in a non-concerted hydrogen transfer, 2-hydrogen transfer, where you have a radical here in a ferric hydroxide and the tyrosine hasn't donated yet. That doesn't accumulate. We don't see that. But chemistry and intuition says it should be there. And this is where calculations would say, is it reasonable for a ferrule to pull a hydrogen off concertedly with the tyrosine donating the hydrogen? And I think the answer is going to be no way. I think this state is real, and in fact, we think it actually causes the substrate to do this butterfly motion, which sort of locks it in to that place. So Wei Chen is going to talk about this along with Amy. All right, so now I forecast the simulation. That's really the most important way to analyze stop flow data, and once successfully done, immediately translates to analyzing any other kind of data where typically in a freeze-quench EPR or freeze-quench-Mossbauer or chemical quench flow experiment, you have species concentration. That's a difference between absorption experiments where you only have absorbance, and that's a convoluted function of all the species present and their molar absorptivities, right? These other methods have species concentration, and that's trivial. So once you get the stop flow data and you get a simulation that can nail those, the rest of it is easy. So what Ken points out in his review is that the last time this topic was reviewed in the enzymes, which was probably 1950, no, I think it was 1970s. The chapter dealt largely with solution of differential equations necessary to interpret transient kinetic data. So all those equations I've shown you, that's solving differential equations to say, how does a species evolve in time in a given mechanism? But you got to know the mechanism, right? And some mechanisms are too complicated to solve, so you can't get the analytical solution. So he said that the need to fit data to an explicit solution greatly restricted the design of experiments, and equilibrium perturbation methods were preferred in large part because of the ability to linearize, this is terrible, don't ever do this anymore, differential equations describing systems near equilibrium. All of that has changed due to recent advances. Now, this is 1992, so it's not recent anymore. In computational methods, one is no longer restricted to simplified reaction schemes or tied to tedious analysis of differential equations and seeking solutions of rate equations. Experiments can now be performed without restrictions for the starting conditions. Anyone know the term pseudo-first order? So this is a way to take a reaction that's second order, and by having one reactant present at such a high concentration relative to the other that its concentration doesn't change in time, and it looks now kinetically and mathematically like a first order reaction. That dominated kineticist thinking. We had to make everything pseudo-first order. We simply don't have to do that anymore. And so experiments can be performed without restrictions for starting conditions of the experiment dictated by the easy solution of the rate equations, and the results can be analyzed by fitting of data directly to a kinetic scheme. And it's the math behind this is ridiculously trivial. It's just algebra and updating, okay? So you could write a program. I promise you, anyone in this room could write a program that does what Kintex Sim does. But this has evolved over many years, and it's slick as heck now. So it's worth, to me, it's worth the $1,000 if you can afford it. All right, so let's look at isopenicillin N synthase. I told you already that this complex mechanism collapses into really 5 states, where this one actually turns out not even to be on the catalytic cycle. That's the resting enzyme, and you got to bind the substrate once, but then you crank around this way. You ignore that guy, okay? And Esta Tamanaha figured this out. Here's a complicated and, I know, uninterpretable kinetic mechanism, but that's what actually emerged from her detailed, in-depth analysis of her kinetic data, really for just one species in time, under many different types of experiments, different reaction conditions. She followed the ferrule intermediate exclusively. And from that, she figured out a couple of really interesting things. One is what I've been telling you, that the enzyme that emerges from the catalytic cycle binds substrate about 10 times, 20 times more rapidly than this resting enzyme that we prepare by isolating the apoprotein, adding ferrocyanine. We can then measure substrate binding to that, and it's slow. But coming through the cycle, it binds much faster. Never would have seen that without in-depth analysis. I'll just run you through that real quick. It's a nice example. So Esta, most of her experiments involved making the complex and shooting it with oxygen. And the ferrule intermediate, characterized by this absorbance at 515 nanometers, forms fast and then decays. She could do an experiment where she mixed first with oxygen. This is just a technical detail. Basically, she's mixing with oxygen and substrate all at once. The difference there is oxygen adds last. It's ready to go in syringe A in this experiment. In this experiment, it has to first bind the substrate, then react with oxygen. So there's a delay caused by needing to bind the substrate, and that gives you this longer lag, right? So she could do fitting here. Here are the equations. You've seen them before. She fits this, and she gets a rate constant for oxygen addition under these conditions. That depends on the oxygen concentration, but under this oxygen concentration, 60 per second for addition of oxygen. In the experiment where she then mixed together, it's now, the ferrule is now C, because A is the protein with the iron but no substrate, B is the substrate complex, and C is now the ferrule. When she started here with the substrate complex, B is the ferrule, okay? So now here's the more complicated equation, and she fits this and nicely hits that lag, and that gave a substrate effective first-order rate constant for binding of 4 per second, and the concentration of substrate here was 8 millimolar. So the second order, and we didn't verify that explicitly that it is second order, that it has second-order behavior. That's important. We need to do that, but we haven't yet. But it predicts a second-order rate constant of 0.5 per millimolar per second. So then Esta did this series of experiments, and she has substrate present from 0.5 to 16 millimolar, and oxygen is about 0.9 or 0.8 millimolar. So in this case, the limiting reactant is actually the substrate. The enzyme doesn't react with oxygen well without the substrate. It triggers it. So you see what looks like a simple rise-fall. When she's at 16 millimolar now, the enzyme was only about 100 micromolar here. Oxygen is about 800. It has to do 8 turnovers or something like that. I might not have that right. It might be 4. So look at the trace you get with lots of substrate. It's bizarre. It goes up fast. That's the first turnover. Then it wants to start to come down, but then once the intermediate decays and product release, substrate binds again, oxygen adds again, the intermediate reforms, and you get this plateau. Okay, and now it kind of extends out for a while, but then you run out of oxygen and it drops off the map. So what's the equation to fit that? Yeah, it's hopeless. No chance you could ever solve the equation for that. But you don't have to. You plug it into a Kintex sim with the right mechanism, and that's a global simulation of all those traces with a single set of rate constants. So not bad. But what it told her was that, and she almost pulled all her hair out over this, was that the rate constant for substrate binding is about 12 per millimolar per second. It's the only way you can analyze these data. I mean, it absolutely is tightly constrained. And in the experiment starting with the resting complex, it was 0.5 per millimolar per second. Well, that means that, this binding step cannot be on the catalytic sequence. It just doesn't work. And so Esta then looked at the crystal structure solved by Baldwin and coworkers and found that there's this glutamine that coordinates. It's a weird ligand for an iron site, right? But there's a glutamine at the C terminus that coordinates. And when ACV binds, it displaces that glutamine. And so what she reasoned is, I think, logically, although it's just a testable hypothesis at this point, is that once this product forms and releases, that glutamine doesn't re-coordinate. And so when you're starting with resting enzyme, it's there and you got to get rid of it. But coming through the sequence, it just hangs out and the next substrate binds without needing to displace that. And she never would have found that without digging in and analyzing these data. And I point out that what she saw was she's watching the evolution in time of the concentration of an intermediate that first forms in a single turnover and then, kind of hangs out and decays in what amounts to a pseudo-steady state over about 5 turnovers. So it's neither a steady state experiment nor a single turnover experiment. And it's not monitoring the product either. It's monitoring the cofactor. So it's really kind of weird. But the fact is that, as you might guess, if you get a trace that's this structured, it drives you crazy to analyze it. But if you succeed, there's a spectacular amount of information in that curve. And that comes out of analyzing by Kintex. Okay, so I'm not going to get to any examples, but that's good because one of them is Car C, and Wei Chen's going to tell you all about that, and Amy when they talk in the symposium. But here's what Kintex Sim looks like. So it runs on a Mac or a PC. You open it up and you see this screen. And Esta made these for me, so I'm not sure exactly what's going on here. But so here's where she's typing in the mechanism, and that's pretty simple. E plus S, that's the substrate binding step. It goes to A, that's the complex. A then binds oxygen, goes to a ferric, that's the ferric superoxide, goes to the iron 4, goes to the enzyme product complex, and then it releases product. Okay. So here she shows what comes up when you go to enter rate constants. The defaults are 10 and 1. I don't know why. That's what Ken put in there. Here's the mechanism. You got to enter rate constants for these. Here's what it looks like graphically. You could have branches and interconnections, but we don't here. So here's some data. She can enter the data in, import data. You need it in a special format, but it's trivial. You can just cut it and paste it out of any spreadsheet program and add a couple of things, and Kintex Sim will read it. S1 is what you multiply, some factor you multiply a species concentration by to try to reproduce the absorption curve. And that's just the molar absorptivity of that intermediate, right? So the output here is species concentration because here Esta entered the substrate, the complex concentration, and oxygen. So initial concentrations. But here she has absorbance data. So she has to relate the concentration of the iron 4 intermediate to the absorbance by the molar absorptivity F1. So that's a parameter you have to enter in. But if you're simulating species concentration, it becomes irrelevant, right? It just goes to 1. All right, so here's the trace she tried to simulate, and here's the simulation. Here are the rate constants she's entered. And what she then is trying to show me here is the fact that, sorry, I have to remind myself what she's trying to show me. Okay. She was able to see that, I think I'm missing one here. Yeah, somehow one got deleted. That's bad. So in trying to analyze the trace where she has limiting oxygen or limiting enzyme, what she realized is the enzyme, she could see that it's only 70% active. So, we know oxygen concentration in this experiment, and so we get a set of traces. When she went and kept the oxygen low and the enzyme high, what she realized was the enzyme was only 70% as concentrated as she thought. So that told her there had to be 30% inactive. And that's what I'm telling you. You'll see this. If you do the right experiments to see it, all these recombinant enzymes will be fractionally active. Very few of them 100%. Some are as low as a few percent, unfortunately. So, and then another thing, this is the one where if she had the concentration of enzyme she thought in the enzyme dependence, she didn't reproduce the traces with the same rate constants. But if she reduced the enzyme concentration to 67%, it fit nicely. And then she shows me this shunt pathway where a fraction of the enzyme goes from the resting state and adds oxygen and goes to some sort of ferrous state that didn't make product, didn't go through the iron 4 intermediate. And so that seemed, I was skeptical. I was like, okay, that's a fudge factor, right, is what that is. Then we look in the Mossbauer and we see that one type of ferrous rapidly converts to another type of ferrous, and we can quantify that. And I was like, oh my gosh, that's, So it validates the analysis. And this all comes from just probably a year and a half of almost killing herself, just trying to get every trace from every experiment with a single mechanism and a single set of rate constants. Okay, so I'm going to stop there since I'm out of time.